things. Let's consider some vectors. Let's say A equals 2 and 1 and B equals 5 and 3. And now let's consider the idea of the span. And let's say that we also have some vector C, and that vector is equal to 7 and 1. Now, what the question could be is C in the span of A and B? In mathematical language, it can be written as does C belong to span of basically A and B, where A and B are vectors? Well, this is a good question, and in this video we'll look at how to figure out. So basically a span is the collection of all linear combinations of some vectors. So we're given some set of vectors. Let's say that this set will be called capital A, and this set consists of vector A. So we can write in this column notation. We can keep running like this, of the vector 2, 1 and 5, 3. The names of these two vectors, of course, we've written. So in such, when we already define like this, we can say does C, this vector C, this third vector with the same amount of entries but different values inside those entries, does it belong to the span of this A, where A is a set of some other vectors. So when we have a set of some vectors, all the different linear combinations of them form the span of them. So we can take, let's say, some vector B, and it will be equal to k1 times the vector A plus k2 times the vector B, where k2 and k1 and k2 are some arbitrary any scalars, and D, the vector D, will be all the different, D represents all the different possibilities, all the members of the span set of A and B, all the different vectors that come about when we take vector A and vector B, put them together as a linear combination, where a linear combination basically just means add up these two vectors, but each of them can be multiplied by whatever scalar quantity. Let's say we add up A and B, but A will be multiplied twice and B will be multiplied by pi. As an example, that belongs to the span. Now, how do we determine if some other third vector also belongs to the span of these two vectors? Well, first of all, this is the posed question in math language, and the way we can solve it is basically we can create an equation that describes the situation that the span of vectors brings about. So vector span basically means we want some vector, and in this case we want to check it for C. So we want to see if C actually can be written as a member of the span of A and B. That's what we're doing when we're looking for an answer to the question, is C in the span of A and B? So what I can do is create an equation. Before we said that span is all the vectors that we can call D. Of course, they represent different vectors under different scalars on the other side of the equation. That satisfy that we can take some two scalars K1 and K2 and apply them to the two vectors that they form the span of. So 2, 1 and that's A, and 5, 3 is B. So whatever these two values K1, K2 are, all the different options that they are will all create different results for this vector D. And all these different D's will be members of the span set, basically. It's also forms like infinite set. So in this case, we actually want to verify for a concrete vector. The question was, does C belong to the span? So I'll put the C, a concrete case, on this side. And what I want to check for is there a solution to this equation? Well, now, if one is already used to this kind of question, one is quite possibly able to instinctively go to the second step and form two linear equations and check if there's a solution for this system. How that comes about is we can visualize it in the following manner. We have this vector and this vector. They have two entries. Let's say A1, A2 and B1, B2. Then for scalar multiplication of vectors, it means that both of the entries get multiplied by the scale. So I can rewrite this as the first entry and the second entry, the x and y entries. We can say this is all, the top ones are x entries, the bottom ones are y entries, for example. 7 and 1 on the left side stays. And on the right side, let's put the scalars inside the vector column. So we'll have 2k1 and 1k1 plus, and again just basically put it inside the vector already. It's 5k2 and 3k2. Then we can use another rule that applies to vectors, especially like even adding matrices, adding same size matrices, column vectors, or column matrices. What applies here is we can add up these components together and put them into a single vector. So what we get out of this is 7, 1, this vector with 2 entries, 7 and 1, equals to add up the top part, 2k1 plus 5k2, it's the top part, and we just make it a single column vector. Now it's y, but it's just one entry, so it's 1 by 2. So 2 rows and just one column still. 1k1 plus 3k2. So these are the 2 entries on the right side. You see how it got added up. And now, for vector, again, another rule to keep in mind here and use is we can make equal the corresponding entries. So the x entry on the left side and the x entry on the right side should equal just like the y entry. That means 7 will equal this, 2k1 plus 5k2, and 1 will equal k1 plus 3k2. So now this is the way we slowly go to the system of linear equations. That when one is used to this kind of examples, one instinctively creates this linear system quite quickly without much hesitation, or doesn't take time because one already knows how it continues. One can see, oh, we have entries x and y for both. We're looking for c. Well, that means that 7 must equal 2k1 plus 5k2, and also 1 should equal 1k1 plus 3k2. That's basically the idea here. But of course, with that equation with the vectors, it was explicitly shown how that comes about, that idea. So now we have these 2 linear equations, and if there is a solution, that means that yes, it does satisfy, and indeed this is true. This will be true if this has a solution. If it does not have a solution, or also it can have infinitely many solutions, then if it has infinitely many solutions, that's similar to if it does have a solution, but if it doesn't have a solution means that C actually is not in the span of the vectors A and B. So let's look at it. First of all, I see k1 here as a unit multiple, so I can say k1 equals 1 minus 3k2 by just subtracting 3k2 to the left side, and I put that k1 value into the first equation to get k2. So 7 will equal 2 times k1, where k1 is this. Usual solution for a linear equation. So what we get is this. Perhaps we can take away 7 on both sides, or we can take away 2. So 5 will equal to minus k2. And thereby k2 will equal minus 5. And then we go back to this equation when there's a relation between k1 and k2. So thereby k1 will equal to 1 minus 3 times minus 5. So it's minus 14. Or actually, minus 3 times minus 5 is plus 15. So it's actually 16. So k1 is 16 and k2 is minus 5. So we do indeed have a solution, and the solution is as follows. K1 is 16 and k2 is minus 5. That means that yes, C2 does belong to the span of the set A, that is basically the vectors A and B. And why? It's because we can write C, which is 7, 1. We can write it as a linear combination where k1 is 16, so 16 times 2, 1. Minus 5 times 5, 3. We can use these 2 scalars and combine the 2 vectors in the following way, such that we create a linear combination of A and B, which yields C, and thereby we can say that C does belong to the span of A and B.